Okay. So hello, everyone. Welcome to Recitation 2 on Mechanics and Materials 1. In this recitation, we have also 4 questions to go through together. And as always, please feel free to interrupt me if you have any questions or if something is not clear. Can you hear that? Can you see that well? And can you hear me well? Okay. All right. So the first recitation, or the first question that we want to look at is similar to problem 3.122 of the book. A mechanic uses a crowfoot wrench to loosen a bolt at C, so this bolt here, and the mechanic holds the socket wrench handle at point A and B and applies forces at this point. So these are 2 unknown forces. Let's say this is force A, maybe, and this is force B. We don't know the components. We know there are 2 forces. And then we know that the equivalent force couple system of whatever is applied here, its equivalent force couple system, there would be a force C here, and there would be a moment M here, or MC here. MC is given, and C is given. Okay? So we don't know what is A, we don't know what is B, or those 6 components, these are unknowns. But we do know its equivalent force couple system at point C. So we know its effect, or their effects. And you are asked to determine the forces applied at A and B when AZ is 2 pounds. The force is not given in Newton here. It's basically pound or pound force, if you want. But that shouldn't be a complication here. So we just pay attention to the numbers. All right, so the problem is not really difficult. It's a calculation problem. Remember what we did when we wanted to talk about equivalent force couple systems. So equivalent force of multiple forces is the sum of the forces. And let's say equivalent couple would be the sum of the moments of those forces with respect to point C, okay? With respect to point C. And usually we do not use the subscript C in this manner. So when you use a subscript, you should explain why you do that. Sometimes it means with respect to a point, sometimes it means at a point, right? So here the book has used it, or this question has used it as the point moment, okay? Which again, because it's a pure moment, you can shift it, so it also means it's with respect to. But in order to make sure that you can distinguish between the 2, I also write it more clearly on the right-hand side. But what I'm trying to say is that these moments that I'm talking about are the moments of these forces with respect to point C. They are not the moment that we had previously at point C. All right. So that's really it. So these are the 2 equations you need to solve. By the way, usually our task in static is to set these to 0, okay? This is not what this question asks. So this is equilibrium, and this one is just equivalent systems. Okay, so this is letter V, this is letter L. So these are 2 different things. Usually we talk about equilibrium, but for this particular problem, we just want to talk about this equivalent system of forces and moments. Okay, so we start from the first one. So we know FR, so equivalent force, which in this case would be C. This is the force C. It would be force A plus force B. Okay, again, remember force A and force B are basically these 2 forces here. So there would be a force here that maybe you call it force A. So that is the force vector, and this is the force vector. All right, so this is just the first equation you have, but this is a set of equations. So this is this looks like one equation, but it's obviously three equations. So this would be Cx in I direction, Cy in J direction, Cz in K direction, and you have the components of C. So this would be minus 8 I plus, let's say, 0 in J plus 4 in K. So that's C. For A, this would be AX in I plus AY in J plus AZ in K. It just happens that also the question tells you AZ is 2. So you can insert 2 here. And we will do it in the next step. But for now, let's just keep it as parametric. So this would be the same thing for B. B is also made of 3 components, Bx, By, and Bz. Okay, as I mentioned, now you get 3 equations, basically. So these 3 equations, if you want to just write them together, this would be, the first equation would be Ax plus Bx equals 8. Sorry, equals minus 8. Okay? That's the first equation. The second equation is Ay plus By is 0. The last one is Az, which is now 2. So instead of Az, I'm going to write 2 plus Bz equals 4. All right, so these are 3 equations for now. Remember, just naively speaking, you can always think that you have 6 unknowns. It just happens that you know what is Az. So we know it's 2. So for this problem, you have 5 unknowns. But just, you can imagine this was also an unknown. And then you have your first 3 equations. We still need 3 more equations to calculate, let's say, the 3 remaining unknowns. Okay, so that is your force equivalence. Now the next thing you want to do is to also play with the moment equivalence. Now the moment equivalence is not very complicated. Again, what you need to do is to just think about this. So let's say you have a force at A, which we call it force A. Now the distance with respect to point C times the force A would give you the moment from this force, right? And then you do the same thing. So the distance from point B times the force at B. So that moment at C is the distance CA times force A, cross product, because it's the moment, plus CB, these are vectors, obviously, times B. All right? So that's what you have. And then we know what is MC. We know what is CA and CB, because we have the geometry. We have all the dimensions in the example. And then the unknowns are, again, condensed within A and B. So that's what you need to write next. All right. For doing that, then I will just, let's say, express the same equation again. You would have R of A with respect to C, this is exactly CA, times force A plus R B with respect to C. So this is the distance from C to B times B. This is equal MC. All right, so what you need to do now is to just, let's say, expand these relations. You know, these cross products, they come into these determinants, or you calculate them using these usual determinants. So here you would have I, J, K, I, J, K. Now, RAC, sorry, RA with respect to C. So this is A with respect to C, which means this is equivalent to CA. it's basically this vector. You can immediately see that vector does not have a component in the y direction. It just has a component in x direction, so you come 8 inches in x direction, and then you come 8 inches in z direction. So it's 8, 0, 8, something like that, right? So you would have that. This would be 8, 0, 8. And the force A, it's AX, AY, and AZ, but then AZ, we know it's 2. And then you do the same thing for B. Again, if you just look at the picture, you can see you go 2 units backwards in Z, and then you come 8 units forwards in X. So that would be 8, 0, minus 2. And that's exactly what we are going to write here. So this would be 8, 0, minus 2. And then you have BX, BY, BZ. And then that would be equals MC, which in the question, you know, it's 360 in the I direction. Okay. So again, if you do this multiplication, you get basically 3 equations, 3 unknowns. Before doing that, I also want to just, sorry, you don't get 3 equations, 3 unknowns. You would have obviously more unknowns, but together with the other ones, it will work. But before doing that, let's just look at this. From this one, you can see that BZ is also 2. Okay? So before doing the calculations, let's also put 2 here to simplify our lives a little. So I'm going to just put 2 here. Then you have less unknowns to just calculate these cross products. Okay, so you would have something like 2by minus 8ay in the I direction plus 16 plus 2bx plus 16 minus 8ax in the j direction and plus 8by plus 8ay in k direction. That altogether is 360 in I direction, okay? So basically this tells you that, or this gives you also 3 equations. So you would have additionally these 3 equations. The first equation is that this is 360. So 2by minus 8ay is 360. 32 plus 2bx minus 8ax is 0, and 8by plus 8ay is 0. Now, if you look at the last one, this basically tells you by plus ay is 0, which is the same as this one. So not a big surprise really there. Okay, so these are also 3 equations. Now all you need to do is to calculate the unknowns. You have all the required equations. And if you do that, your A would be, or let's say vector A would be 1.6 in I direction minus 36 in J direction plus 2 in K direction. And B would be minus 9.6 in I direction. So remember, these 2 together should be minus 8. So if A is 1.6, B should be minus 9.6. Then AY and BY are opposite, so that would be plus 36, and the last one we knew it was 2 already. Okay, so that's it. We know exactly now the forces. This is the solution. Is that clear? Do you have any question? All right, so now with that, we can come to the next example. So here is the problem. You will have a weight hanging, let's say, from this beam. The beam is attached here by, let's say, a pin or a hinge, you know. So it's something like that. It's a hinge which can apply 2 forces but no moments. So you can imagine there are 2 reaction forces here, but there is no additional moment. And then you have a cable here, so naturally you can imagine along the cable you would have a tension T. And here you would have the weight W. And here I'm writing W as a vector W, which would be W times, let's say, G downward. You know, that would be the vector, it would be downward. Okay, so we know this. You are asked to calculate the tension in the cable and also the reaction at point B. Now, there are 2 ways of solving this. One is like a geometrical shortcut. I personally do not necessarily encourage that, but some of you like it, and also in the solution manuals you see that. And you know, just to have that covered, I first show you the shortcut way. And it's pretty nice. So in terms of, let's say, explaining the physics of the problem, it's nice, but I think it's not always very, very reliable. So under exam stress, I think you should go through a straightforward ways rather than shortcuts, maybe. Okay, so here is the way. If you just think about this, so let's cut this piece. What are the forces acting on it? You know, so what are the external forces? There is this T, there is a weight, and then there is a force B, which we don't know its direction or magnitude. But we know there are 3 forces, right? So the fact that you know there are 3 forces, it gives you a lot of information. So the first thing is that, let's say, if you draw this T along this line, so let's say this is your T, and then this is your weight. If I continue this line, you would cut it at this point. Let's call this point E. Now, the reaction force at B, it has to pass through this point, right? Otherwise, if it doesn't pass through this point, that means with respect to this point, it will cause a moment, which is against equilibrium. So basically, you know that your reaction force at B, it must be in this particular direction. So let's call that vector B. It's a bold B. Now, obviously, we don't know this angle yet. But from the problem geometry, we can, let's say, solve that angle, okay? Let me just solve the angle, and then we will discuss about the physics of the problem. So if you just look at the picture, you can continue this line, and then you can continue this line. So this distance here, you see it's 0.4, and the distance here is 1.4. So the whole thing is 1.8. But if you look at the point E, so let's make a third cut here. Let's say here. Then the lower distance is basically 1.8 minus, let's call it D, and d being the distance above. Okay? Now, the distance above, how much is that? How much is this distance? Or let's think about it this way. If you think about this angle, or even the 50, okay, this is angle 35. Maybe it's easier for you. So if you look at this angle 35, that distance d divided by a is tangent of 35, right? A is this, which is the same as this one, right? So that distance d divided by a is tangent of 35, and a is 1.5 meters. So from that, you can calculate d. D is going to be 1.0503. Now, if you have that, then 1 minus 1.8 minus d would be 0. Let's say 7.5. Let's simplify the digits a little. Does that make sense? Okay, so now that we have these, let's say the dimensions, you can immediately calculate the angle beta, right? So now, if you look at this triangle, you know, let's say the distance in front of angle beta, and then you know the distance on the side of angle beta. So you know tangent beta is going to be that 0.75 divided by 1.5. That would be, well, almost 0.5 or 1/2, which gives you beta to be almost 26.5 degrees. Does that make sense? Okay, so this is purely geometrical, but the reason I'm doing this is that for the next step, that is the shortcut that I'm talking about, we need this. So, all right, so now you have a system, you have 3 forces, and you can imagine if you have 3 forces on a system, these 3 forces must make a triangle together to impose equilibrium, right? So let's think about it this way. T plus W plus B must be 0, right? So this is just summation of 3 vectors. So this is my vector T. My vector W is downwards. And then my vector B has to look like this now. It came a little wrong. This angle doesn't have to be 90 degrees. In the drawing, it looks like 90 degrees. But it's not, obviously. So now you know exactly this angle, which is beta, and we just know it's 26.5. And also now, if you look at this triangle, you can use your usual triangle relation, which basically states the following, that let's say T divided by the angle in front, the sinus of the angle in front of it, so this one, which in this case would be 90 degree minus beta, and that would be, well, it would be 63.5 almost, but it doesn't matter. So T divided by this sinus of 90 minus beta is equal B divided by sinus of 55. So this angle is 55, right? And that is equal W divided by sinus of the angle also in front of it, and now that angle would be 61.56 almost, or 55, let's say. So this is this angle. Again, the drawing is a little misleading. It looks like 90, but it's actually 60 almost. So now this relationship is basically two equations. So from this part, you can calculate B, right? So you know what is W. W is weight times gravity, so it's 50 times 9.81, if you want. Okay? So from that one, you can calculate B, and then from this one, you can calculate T. So if you do that, you would have T equals, let's say, 499 almost, and B equals 457 almost. All right? So this is the first way of doing this. And it's perfectly fine if you prefer to do it this way, but also now I want to do a more familiar way of doing it, so not this geometrical shortcut. Okay, so now we look at the same problem again. Let's think about it this way. If again you cut the system the way that we just said, and we write the moment with respect to point B, then we get an equation that does not have the unknowns at B, right? So remember, at B, we have two components, maybe B, Y, B, X. We don't know what they are. Now, if I write the moments with respect to point B, and I set that to 0, this is our equilibrium equation, none of these two unknowns will enter the equation, right? So this is like a little trick that you can always think. When you write moment equation, the point with respect to which you write the moment, the unknowns at that point, they don't enter, right? The forces, they have zero arm, basically, so they don't end that. So basically, if you do that, then you end up with a system which has only two unknowns. One is the T itself. So it's exactly the same thing that we had before. And the other one is just the weight. Now, with respect to point B, the moment of T, the moment of tension, would be the orthogonal, the shortest distance from point B, right? So there is this line that you can just draw here with, let's say, 90-degree angle, and let's call that distance now D. Now, with respect to point B, if you multiply this distance times T, you get a moment that is clockwise, right? So it gives you a clockwise moment with respect to B. And then if you look at this weight, you can also multiply this distance, which we know is A, times weight, and this gives you a counterclockwise moment. And that's everything. So basically what you have here is A times W. Again, by W, I mean the force W, which is 50 times G, and G being 9.81. Okay. A is just 1.5. That's the distance. This is your counterclockwise moment with respect to D. That should cancel the distance D times T itself. So this is the unknown. And now the only thing you want to do is to find D. Okay, so this is a simpler problem to find D now, because you can work with this little triangle here, and it's not too bad. So if you just look at this triangle, D would be 1.8 times sinus of 55, right? 1.8 times sinus of 55. All right, do you have a calculator to do this number? Okay, actually, I should have a calculator too, but no, this doesn't help. If anybody can tell me this number. What was it again? 490. Yes?
It is 1.47.
Thank you. Okay. So I think if the rest is correct, then that should give you a T. All right? So this is another way of doing it, basically. And then once you have T, now you write your, thank you very much. Now you write your equilibrium of forces. So from your equilibrium of moment, now you got the T, the tension itself. So now you can do equilibrium of forces. And from that, you can get your Bx and By. So this would be something like Bx, I don't know, plus Tx is 0, because W does not have a Y component, and then you would have something like By plus Ty plus W, which is minus 50 times G equals 0. So from these, again, you can also get your Bx and By. All right? So either way it works. Again, the second way is more like the way you know it, equilibrium of forces and free body diagram. The first way is more geometrical, but either way, it's fine. Do you have any question? Is that clear, everything? All right. Okay, so the next exercise is similar to problem 4.95. So we are on chapter 4 of the book, basically. You have this axle here supported by two bearings at points C and D. And then you have a pulley here at the end, welded to it. And on that, you apply a tension T. Or let's say there is a cable around it, or there is usually like a conveyor belt, and then you apply a force T at that end. Assuming that that force is purely horizontal, so it has only X component, and then there is this force at the end of the arm AB with 720 Newton downward, so in the Y direction, but with the minus sign. You want to compute the tension in the cord and also the reactions at C and D. Now, at C and D, these are bearings. Usually, you would expect to have 3 components on each. So this would be, remember we said bearings, they do not usually apply moments, right? So there is no moment. There would be CZ here. There is CX, CY, so 3 components from C and 3 components from D. Again, dx, dy. But dz, the problem tells you it is 0. So the bearing at D does not exert any axial thrust, so we can omit that. So this is the system we have. Again, if you look at it, there are 6 unknowns. And what you want to do is to calculate that. So you want to calculate the tension in the cord first. Now, there are also many ways to do this. If you look how many unknowns we have at C, there are 3. If you look how many unknowns we have at D, there are 2. So let's say one way that you can start this is to write moment with respect to d is 0. Okay, and then of course you would need some of the forces to be 0 too. The other way maybe is to start from moment with respect to c being 0, and then of course again some of the forces to be 0. But now you can imagine if you do the second one, when you write that, you would have less unknowns to deal with, right? So by writing the moments with respect to c, we will not see any of these in those three equations. So you would end up with a system which is three equations, three unknowns. Okay? So this makes more sense to do it like that rather than the first way. If you write it with respect to d, then you would have four unknowns eventually and three equations, so you need the fourth. Does that make sense? But also, there is a third way, which I'm sure you can see that. So what if you write the moment with respect to CD? It's a scalar, but remember, we could also write the moment not with respect to a point, but with respect to axis. So what if we write the moment with respect to axis Z, or the line CD? Then you can immediately see that none of these will enter the equation, right? Because they have zero distance from that axis. So you end up exactly with just one unknown, one equation. Maybe that's the fastest way to get the attention. Okay? So I'm not going to do this. I will write this first, and then I will write also this shortly afterwards. But then again, there is usually not a single way of solving this. No matter what you do, if you are careful, you should get to the solution. Okay, so if you write some of the forces with respect to C is 0, sorry, some of the moments with respect to C is 0. Now, with respect to C, you would have the forces at D, and the distance, so there is CD times force at D plus CA times the forces at A, and then eventually the force T. So if I think this point is maybe, let's call this point F, then there would be something like CF times force T. The sum of all of this should be 0, okay? And now if you just write this, or if you spell out CD, you can see CD is a vector opposite of the Z direction. So that would be in the minus direction, 120 millimeters. So that would be, let's say, minus 120K. And the D itself is just, these are unknown components. So dxi plus dy j, and then there is no Z component. So it has two components. Then you have CA. So again, looking at CA, there is 80 millimeters in Z direction, 200 millimeters in the opposite of X direction. So that would be plus 80K. Can you hear this noise, or is it? There's like a vibration or something. Okay. So there is some 80K minus 200I times minus 720J. And then eventually you have the one from the cable itself. So CF would be 120 in J direction or in Y direction. So that would be the radius. That's how much you come up. And then this much you go backwards, which is 160. So 120 plus 40. So that's 120J minus 160K times T, and then T itself is purely horizontal, so it has only I components. And that's it. So let's put this also in bracket. That's what you have here. So if you just look at what is in front of you, it's three unknowns here. and again, 3 equations. So in x, y, z. So if you do the cross products correctly, I'm not going to write it down because it just is very simple. It's just calculations. But if you do it right, from these 3 equations, 3 unknowns, you can get immediately dy is minus 480 Newton. T is 1200 Newton. And dx is minus 1600 Newton. All right? Now that you have the sum of moments with respect to C, the next thing you want to do is to just write the equilibrium of forces and find the remaining unknowns, right? So that's pretty simple. So basically, you would have the forces that you have is C plus D plus T as a vector, and then you would have this 720 downwards in J. So this must be 0. And then at this point, you have already D, you have T, and this is, again, known. The only unknowns is C, and all the 3 components of it. So you would need to find what is Cx, Cy, and Cz. And if you do these little calculations from the components, you have Cz would be 0, Cy would be 1200, and Cx would be 400. All right? So that's that. You have basically solved this problem. Just quickly, because I mentioned you could also alternatively write the moment with respect to CE. That's pretty simple. So just think about it. Let's look at this. If you think about this, the moment with respect to this axis. So we want to write the moment with respect to this axis, right? So none of these will cause a moment because they don't have a distance. And the other forces that are there, you are looking for their perpendicular distance, right? So with respect to this axis, the perpendicular distance of this tension is 120 millimeters. So you actually have that 120 millimeters. So you get a, let's say, a clockwise moment due to this, right? So you get something which looks like minus 120 t. I put minus to emphasize it's clockwise. And then that's that. And then from this one, the distance is this, which is 200 millimeters. And the force is 720, and it's counterclockwise, right? So it will cause a moment which looks like that. So it's counterclockwise. So plus 200 times 720 equals 0. And you can clearly see this is just one, and then again, plus here means it's counterclockwise. You can immediately see this gives you T equals 1200 newtons. Does that make sense? Okay, so that's that. Any question? All right, the last problem of today is kind of similar to what, or is a combination of what we did in the previous exercises. It's basically a 3-dimensional equilibrium problem, and the idea is very simple. You want to use a combination of your equilibrium equations and the problem geometry to solve this. Okay, so it's again a very usual exercise for you, except it has a little trick here. So you have the given system. There is this pipe ACDE, which is supported at A and E by ball and socket joints. So these ball and socket joints, they are just like hinges or pins in 3D. So they can apply 3 let's say, 3 forces. So for each of them, you would have 3 unknowns in principle, okay? So that's that. Now, you support the system by the wire DF. So there is this wire, and then there is this DF. And then there is this external force that you apply here downwards, 614 Newton. You want to calculate the tension in the wire. Okay, so we can start as usual, but if you go as usual with this problem, it's not going to work. So it's a little tricky in that sense. If you just look at how many unknowns you have 3 here, you have 3 here, and then you have 1 here. So there are 7 unknowns. That means if you just, let's say, carelessly write your 6 equations, you may not be able to solve the system. Okay, so you need to do something better than that. But then maybe you know already, or also combining what we did in the previous problems, maybe you can see what I'm going to do next. What you can do is to write equilibrium of moments with respect to the line AE. If you write moment equilibrium with respect to the axis AE, then none of the 3 unknowns at A and none of the 3 unknowns at E, they will contribute to that equation, right? So you end up with 1 equation, 1 unknown, which is tension. That's exactly what you want, and you can just solve that. Okay? So it looks very similar to what we did at the end of the previous exercise, and that's exactly what you want to do. The equation to use here would be sum of moments with respect to line or axis AE is 0. And it's a scalar value, right, obviously. And that would be the director of that. So let me just draw that line. So assuming that this is the line, the director of that line, let's say it would be lambda AE. So what you want to do is to project the moment of force or the tension T with respect to any point on that line. So you can just project. So this means projection, right? You can project the moment with respect to any point on that line. So a good point in this problem maybe would be point A. So we can do that. That would be AD times T. So that would be the moment of tension with respect to the line. Again, this is the moment with respect to point. This is with respect to point A, and this is the projection thereof, which tells you or which gives you the moment with respect to line AE. That plus, again, the projection of the moment from the force applied at point B. And the force applied at point B is 640 Newton downwards. So it's 640 minus J. Okay, so this is 0. Now, all you need to do is to just calculate these little parts of this. So this is clear what it is. What you need to have is AB, AD. For T, you don't know it. I mean, you know the direction of it, but you don't know. Let's say the component of it, but we can also do that. So all right, so what did I say? I said you don't know the direction. Well, what I meant is that you don't know the magnitude of it, you know its direction. I think I said something wrong. Okay, all you need to do is to basically replace these values. Now, AB here, it's very simple. It's just, let's say, 200 millimeters in x direction, right? So that's 200 in I. Then you have AD. AD is this one, so you go 480 in x direction and then 160 upwards. So that would be 480 in I plus 160 in J. Now, for TDF, again, you don't know the amount of it, the magnitude of it, but you know its direction, which you can calculate like this. And then again, this is nothing but just lambda df, obviously. And also lambda AE is simply AE divided by the magnitude of AE. Okay? So if you kind of look at the coordinate, and you have all the coordinates, so it's very simple to calculate these little vectors. So lambda AE, for instance, which is AE divided by magnitude of AE. This is only calculations from this point on. Once you understand what's going on, this would be something like 6I plus 2J plus 3K divided by its magnitude, which is 7. So that is lambda AE. Lambda df, this would be again df divided by its magnitude. That would end up with something like minus 16 in the I direction, 11 in the J direction, and minus 8 in K direction divided by 21. And okay, now that you have these, simply all you have to do is to just, compute these cross products, and from that you can calculate your T. Again, for the cross product, you need that determinant thing, so I'm just jumping over that step. But if you do that, and if I did not make a mistake, this should be something like that. All right? Okay, so that's that. That's the last problem of today's recitation. Do you have any question? Okay, so